Okay, here's a puzzle for you guys. It's a plot with no labels.
It is not on a logarithmic scale.
Correct. What's that?
It looks similar to the homework. It looks like you've got a giant component type thing going on.
Interesting word. Yeah, right. Okay. Yeah.
It's not a, looks like an energy cost curve.
Whatever it is, something took off, right? Boosh. Yeah, kind of. Yeah, yeah. What do you think the?
Nothing going on the left. And then really nothing going on for a long time, and then you hit some critical threshold.
So you used a word here. You said, "What do you think this is? This axis?"
It's not like
It's not. But what could the units be?
Time or some time related.
Okay.
it can't be time because time isn't ever negative.
Depends which giant religion you're involved with.
Last Thursdays. Something about
The crowd reveals something about itself right there. Yeah. What's that?
is that shutdown related?
No, it's not actually. No. So there's an increase. Generally, it kind of went backwards here for a while, and then back up. All right, it's time. How can it be time?
Time from a certain.
Right. Thousands of what, do you think? Minutes? Years? Seconds?
I mean, it only goes a little bit past 2000,
So
so
this, yeah.
Huge gap in
So it's about human civilization, right? This is something that people managed to do. It's measuring something that people have done over years, all right? So this is BC. This is where we are now, right?
we have more. Does it have to do with written language?
So it's actually, okay, no, it's not that. It's not that. Yeah, tweet volume is 0, and then that's a disturbing plot. I'll tell you, this is in.
I'm concerned about the massive hole in the data.
Yeah. Well, you should. That's humans were struggling for a long time. Then. Yeah. Kind of a. Well, I mean, things. Something we made. Something people made.
Why would there be any Bibles?
So this dimension is just space. It's a length dimension. It's height. It's height of something.
Height of all of human civilization.
Yeah, not a metaphorical height, a real height. Yeah. Okay. So these are the pyramids, and then it's just like nothing, right? The Egyptians are like yes, and what happened here was you get a couple of cathedrals in Europe, and then some of them fall over. They get blown apart in lightning storms and things, and now. I know these are the spires, cathedrals, and so on, right? So they've.
It drops back down to the pyramids.
Yeah, is it back down to them right then?
Or
Not quite.
some of the.
Kind of feels like it's.
Really tall stuff also.
It might be the pyramid again there. Have a look at that. And then we went Barney bananas. Yeah. Right, over the last 100 years. Okay, that was for fun. I'll tell you what, right? This is just the height of the tallest building on Earth as a function of year. But it was a puzzle. Okay, all right. That was funny. Okay. Sorry, I amused myself at your expense. All right. But it's kind of interesting. You can imagine making up all sorts of little puzzles like this. What is this graph? And just getting all kinds of answers. Yeah, right. All right, that was tricky. Okay. So, yeah. Okay, so it's networks. All right, so we've got a lot to talk about with networks, and there are more things to add in. But okay, we're just going to go right into the main properties of complex networks, the things that we think of as complex networks now. All right, so these are generally large-scale networks. They're sparse, right? They're not dense things. There's usually some growing aspect to them. I mean, in principle, networks are just networks, but these are the ones that we've focused on. Okay, so we got to this point that this is a bit of a problem. They're often a horrible mess. So we've got to some very clever work now where we've been able to at least find the big patterns in them. That's a massive body of work, structural detection or community detection. It's been going on for last 12, 13 years. Just massive citations. It's an unbelievable field. All right, so we had this Pratchett. I put the Pratchett in there. Okay, so here are the things that we're going to talk about. And there are more possibly to add or take away and so on. So, but degree distribution, right? So degree is, again, the number of neighbors of a node, number of friends of a node, basic thing. So we call it K. So you take your large network or a big set of networks, and you go through with your graduate student and you force them to do it, and they count the number of friends this one has, and then they count the number of friends this one has, and they make a big histogram, right? Okay, so that's and of course you can look at real networks, you can make model networks that will lead to certain degree distributions. We'll get to that, big thing. Okay, this is all listed. So assortativity, so I'm going to explain all these things, but these two guys go together, it's kind of a birds of a feather, flock together thing. Clustering, so do your friends know each other? This turns out to be a big deal with this whole small world network thing, which is really, really one of these big pieces. Motifs, so they're the small scale structures, right? Or they're repeated patterns. That turns out to be that's 2002 or 3, Uriel Lon's work. Modularity, so this is getting back to the big mess, the big ball, right? The big nasty mess. Is there actually some hierarchical structure to this thing? And, given some network, so it's just a big data file that someone hands you, A is connected to B and so on, all of this stuff, and you feed it into some little machine and it pops out and says, oh, there are 5 big communities and this one has 4 inside it. So there's a huge battle about how to do that at all and then how to do it well, and lots of my approach is better than yours sort of thing. Good stuff. Okay, so concurrency. This is a ridiculous thing, but it's basically that it matters when time matters, right? So if someone is horribly ill and then they talk to you, that matters to you, right? But if they're fine and then they get ill, then it's an issue. So we're only just getting to this now. I'll repeat this basically. We're only just getting to this now. I think in a broad way, analytically, and even modeling, because we like to do this thing I mentioned the other day of just collapse data into make a pretty network, right? Okay, hierarchical scaling, that's could do with modularity, but we'll see that in networks. You're sitting here full of networks that, right, blood networks, hierarchical scaling is going on inside you. Nice product of evolution, river networks, those sorts of things. There are some things that have been floating around in the social networks literature that people have kept, managed to go out and use in lots of areas, even power grids and all sorts of fields, biological networks. So centrality, so how central is a node? So it's a global measure, right? So you're situated in this thing, and this is connected to, say, Google search, for example, right? They want to find the central thing with respect to some sort of query. How efficient are these networks in performing some task, whatever it is? It could be your brain, it could be an organization. And then, so interconnectedness is about connections of different, am I saying the right thing? Yeah, connections of different networks, right? So we can have overlaying networks, which obviously we're seeing. We have social networks, we have economic networks, we have transportation networks. All of these things are going on at once. There are material supply, like energy, water, gas. These are all potentially different networks that could fail really badly in some ways, right? Like you may fail, one of them may fail, but if you have them cascading into each other, really dramatically bad things can happen. So, one of the big examples now is a communication network sitting on top of the power grids that we've built, right? And we're trying to make them smart. All right, so, and then big deal. So we'll see the sort of the great example of evolution of network structure. You have the network evolving, you have dynamics on the networks, and those things are all co-evolving, right? And they could be feeding back lots and lots and lots of craziness. So this is chopped off, isn't it? That's because I can do this. Oh yeah. So this guy with its asterisk is the elephant in the room that we actually can see, right? Which you should be able to see because it's an elephant, right? So it's the elephant. Everyone says, look, it's an elephant. But before the elephant was sitting there, and no one could see the elephant, right? Okay, right. So this we figured out. Okay, so that's the first piece we'll talk about here. We write it as this, P sub k. You've had your problem set. You have some fun with random networks where we're doing this. So you have to think about this properly. Some very odd things happen even for just bare, simple networks, right? So this is you've got your big network and you just randomly pick a node. It's probably that node has degree k, right? It could be such that there are some floating around that have no friends, and so k equals 0 is in the game. This is for unweighted networks, or thinking in an unweighted way, right? This person has 7 friends, whereas in reality, they have 2 really good friends, and they have 3 that they can't, and they have some frenemies, whatever it is, right? So you have some complications. But we have to figure out the bare network stuff to start with. Okay, k is no degree, number of connections, whatever it is. Okay, so this guy you can derive yourself. Right, so Edish Rennie. So this is, right, Paul Eves, very famous character, was on speed the whole time. And you're a perfect mathematician, right? Just unaware of anything else except the speed. Anyway, so all math all the time. Had to sleep, I guess. Okay, so he and others, of course, did a lot of work, beautiful work on random networks. So this is, I don't have it, sometimes I have a box of random networks. So you just take, I'll come back, I'll say it again. But basically, you have n nodes, right? This is all you do. You have n nodes, and you have, in the different ways to construct it, but imagine you have m edges, and you just throw them down, right? Boop. And then you clear it up if there's so many repeats or so on. But you could just imagine, and they're labeled, right? So there's node 1, node 2, node 3, node 4, as we talked about the other day. The labeling matters. So you can imagine there are n nodes, and then there are all these ways that you could have m edges placed on this network, right? So 0 edges, there's only one way to do it. Complete full graph, there's only one way to do it. But in the middle, it's a gigantic number, and we'll talk about that later on, possibly more in complex networks, for those of you who soldier on. Okay, so it's an enormous number of networks. It's just gigantic. It's kind of like the configuration. It's just a huge, huge number as n and m grow. And what this is doing is saying, when we talk about random networks, we just reach into the box and we pull one out, right? And it turns out we never get one that looks like something you see in reality, basically, right? They're all like hiding in a tiny little section of this box, phase space. Like there's a tiny little section, and you'd have to really rummage around to find that guy. But we're doing an odd thing. We're not doing what nature does, right? We're just saying, okay, I have 1 billion edges on 1 trillion nodes, or whatever it is, the other way around. Put them in. Let's find all of those networks, and I'm just going to sample like that. That's not how things are made, right? Networks are made. Okay. But if you do that every time, and it's providing you have a network that's big enough, you get this degree distribution. You get a Poisson degree distribution. Right? If we write. Sometimes people like to do this. You'll see this in the literature, Z for the average of k. So that would be P of k is e to the minus z. So this is just a constant z to the k of a k factorial. Right? So it's a very famous distribution. And maybe you've done it already, but you should be able to get that to arise out of a Poisson distribution as your limit goes to infinity. As the size of the network goes to infinity, providing you keep the average degree fixed, right? That's what stops you from ending up with a Gaussian. Spoiler. Okay. All right. Okay, so that's weird, right? So you might think, given there are so many in this box, like it is impossible for a large enough network size for you to pick out anything that really is distant from this, right? That really has a very different distribution. Okay, so this is a nice little well-controlled distribution. And there's an average degree. Nothing very big, right? Nothing scary. You look at your network and it's kind of, lots of nodes have similar numbers, right? There'll be some with no friends, and there'll be maybe, but you'll never find, you would never see someone that has 1,000 times the average degree in this thing. It doesn't have so-called hubs. All right. That's what these things are. And you know all about parallel size distributions now. And it turns out these guys appear again in networks. Not all networks, but a lot of networks. All right, so, and again, we have these arguments. But scale-free, so-called scale-free networks. This is a bit of a funny word. It doesn't mean if you look at the network and kind of renormalize it like a fractal, that's something you might, that feels like what you're talking about when you say scale-free. This is just about the degree distribution. Doesn't have a scale, right? So we've talked about this. Power law size distributions, right? They have some cutoff. This is an X max, some typical size, X min. You know, there's some messiness in the distribution here and here, but none of the internal scales dominate. It's really the n limits that govern things like moments, right? Okay, good. So that's what we mean when we say scale-free. Of course, it's full of scales. It goes across many, many scales. It just doesn't have a particular one. This one has a particular one. Okay. Okay, so these things have to be built some way. We can, of course, make them up. We can, just force a network to have this distribution and select it. So we can kind of retrieve this behavior where we make a box that's full of scale-free network ones. We can kind of do that too. But that's not organic, it's not growing. So if you have something where the cost of the links goes up or down depending on how you control this cost, then right, this is the sort of thing where someone might end up with 10,000 friends, right? So there are tons of friends. But depending on the cost of links, like, do you really have to talk to all these neighbors? Are they sending you information if you're a human, if you're a I don't know, some sort of interacting thing in some other system? Can you handle that load? That governs how far out this distribution will go, right? Fair enough. But okay. So some odd things about hubs. One of the things is one of the big deals is that they can, of course, make things spread tremendously, right? Because the disease hits a hub, and then depending on how you model this thing. This disease spreading. If you say, okay, it hits this hub, and in the next time step, all of these guys get sick as well. If for some reason this character can kiss everyone or whatever it is that they're doing, well, they shout out their rumor. So it's much more sensible in things like on media, right? That it's modeling that kind of behavior. AP says something bad about Obama, right? This tweet that came out a couple of months ago, and it was the Syrian army that. Syrian something army that had hacked the AP account. Did you guys see this? Yeah, they'd hacked, right, I talked about the other day. They hacked the AP account and put out this little tweet that says, there's a bomb's gone off in the White House and Obama's been hurt. So this is coming from AP, right? So and the market started to go down, and this got retweeted everywhere because, it's AP. So it turns out they were totally hacked. And anyway, but that's the sort of situation where that infection can really, everyone, it's costless, right? It's about this link cost. But if, AP was just a human who had to walk around and tell everyone those things, then that would be much harder. I mean, they could shout, but it wouldn't have the impact. The stock market starts to go down, right? The belief in the United States economy just starts to evaporate because of a tweet. So they deleted it, and things kind of got back together. But yeah, all right. Now, so you'd think, okay, these things are a disaster, and so for certain kinds of spreading, yes, things really spread out. But if there's some limit to the way they behave, if this is Oprah, huge impact, right? She says, buy this book. Yes, I will buy the book. But if you're this person here saying, please tell everyone to buy my book, that's harder to. She's a hub that's going to actually block spreading, right? She's not going to allow everything to come in. So. Depends on the model, right? And a lot of social contagion type models are more in that latter category. Okay, but these networks, this is a big piece. We're going to talk about them in the next set of slides. And it will connect to things we've done before because we've constructed this course in the right way. Okay, so these guys are a mathematical construct, right? They live in mathematicians' heads. Yeah. And they pull them out of that's the box that they pull them out of. Okay. And they're really good fun to play with. But so scale-free ones, on the other hand, are these growing ones. I mean, we've observed them, and that's the explanation we've given for them, and that's the explanation that seems to fit with real data, where we've got enough of the history of the network. Right? It's a plausible mechanism. I've, of course, said all these things before. It's called preferential attachment, but there are other terms for this. Rich gets richer without the poor get poorer part. no gnashing of teeth, and cumulative advantage is the de Sola price approach. Okay, but it's a version of Simon's model essentially transformed into networks. Okay, so randomness is certainly there. It's real, and it's very, there are certain class of random networks that are absolutely key to us for us to model real ones, okay? But it's bad to just start with these so-called pure random networks. Degree distribution is just a monster of a thing. Like one of the best things, a nice thing you can do, usually in analyzing something real is, okay, just take the degree distribution of what you see as done, and then create a box full of random networks, right? Randomize everything else about these networks, except for the degree distribution. So you can rewire it, but if there's a hub here, it stays as a hub. And then see if the resulting set of networks behave as the one individual one you have, this one that you've observed in the wild. And that can start to tell you about how this thing varies from a pure random network with a fixed degree distribution. But you can't just have a big box of networks and try to find all the ones with a certain degree distribution. You will never find them. Okay. Does that make sense? I mean, it's kind of like having all the molecules in the corner of the room. It's a possible state. Statistically, we say that's fine. It's just that the ones that give us this kind of atmosphere, there are a gazillion types of configurations that do that. There's only one that does that. All right, so that's the big piece. And it was just not in our heads until, 1999, 2000. Then everyone got excited. The little piranhas took off. Okay, so very simple thing. Social networks resplendent with homophily, right? So this is, the desire to be with people like yourself in some dimension at least. We'll capitalize on this later on. So one nice mathematical thing that people will play around with, and it seems to have some reasonable merit, is degree, right? So the high degree nodes might connect to high degree nodes or to low degree ones preferentially, right? So you look for that in your system. Is it degree assortative or degree disassortative, right? So that's just a sort of this is an important feature, and it will definitely affect spreading in other ways. So the degree distribution governs a lot about the spreading, and then on top of it you have tweaks, right? So you could have a particular degree distribution, and then you tune the assortativity in different ways, and it can change whether things take off or not, right? So it's definitely important. Okay, so in the case of degree, it's right. If it's assortative, then we have similar degrees. If it's disassortative, we have dissimilar degrees. There's a citation here to a Newman paper. So these ones are often social ones, right? The assortative ones. So company directors, co-authors, actors, right? So actors that have been in a lot of films tend to appear. This seems to be the case, right? We could revisit this, I'm sure. So technological and biological ones tend to have this unevenness, right? So things like, the web type connections and so on, that kind of infrastructure. Protein interactions, which is not a real physical thing, but an interactive network. So a protein that interacts with many others might interact with guys that have few interactions with others, right? And then it goes back and forth. Food webs, maybe in that category as well. All right, so that's an important feature. We can get to that. Okay, clustering. Clustering, big deal. Okay, so this is the central character here, and the question is, it's a way of capturing the local socialness of these networks, right? So if it's completely asocial, then none of your friends will know each other. This is sort of just a first layer kind of thing. You could keep going out. And this was part of the Watt-Strogatz model for small world networks. A big deal. We'll come back to it later. But it was a way of saying that random networks don't work. Just one way of saying that, right? Okay. So your friends tend to know each other. Hopefully that's your experience of the world. So one of the problems, of course, when talking about social phenomena is everyone has their own experience, right? And then so this is a very important thing I have to say. Never try and map your own experience onto large social, systems, because maybe you're right, but usually invariably people say, I'll put up something about, I don't know, like Christmas is bad or something. Like Christmas is a very positive day in our measure on happiness, for example. And then people always pipe up with, but it's a terrible day. Like everyone always fights and you're like, I'm Sorry about your personal life, but it's just very, it's very, people, if you talk about economics, people start talking about, well, I invested in, no, I don't, no, don't talk about yourself, don't talk about yourself. It's like electrons talking about each other when they're, anyway, all right. It's a simple thing, I'm sure you guys are fine. It happens all the time. Anyway, it's embarrassing to watch. Okay, so there are a couple of measures put over time. So the first one was Watson-Strogatz. This is 98, and this is maybe a year or two later. Newman has this nice little, much more cleaner looking guy. And, Morgan's not here, so he can't be offended. But this is a funny way of measuring the local clustering as you go across the network. So in this case, this guy has 5 friends, right? Did I count that correctly? 5 friends. So there are 5 choose 2 ways of those friends of your friends being friends with each other. This can get very confusing to say. Okay, and in this case, there is 1, 2, 3, 4 connections that actually exist. So when we come to that node, what this bit on top would end up with is a 4, because it's saying sum over all of your friends, J1 and J2, that are in your neighborhood. So we're looking at the ith node. So sum over all of those guys. So we take every pair. So we're going to take this pair, then this pair, then this pair, then this pair. Fair enough? Yeah? Neighborhood is your friends. And then this is from the adjacency matrix. So it has a 1 if they're connected and a 0 if they're not. Okay, so we're going to get a 1, 1, 1, 1 for these. Did I get that right? 1, 2, 3, 4. So it'll be a 4. And then there are 5 choose 2. So that's 10 ways of, there are 10 possible friendships that could exist between your friends. So you have, this guy has a local clustering of 0.4, right? 4 out of 10. Okay, yeah. So 4 out of 10. And then you average over everyone. So you go over here and then average over this one. So this guy sees that their friends are connected. From their point of view, these two are connected. Yeah, you have to reassemble a net. Like it's ideally, you sort of pick this guy up, and the network all moves around. And there are some nice kind of visualizations, like the thesaurus one, I think, does that sort of thing. Like you click on this, and it reassembles and makes that the central one. Because this one would have to, move over to here, and yeah. But I can't click on it. It doesn't work. Click. Okay. You have to imagine things. All right. So that's what that is. So it's averaging, it's a global average of a local quantity. Yeah? It means also that if you have a big hub here that has some score, maybe it has a very low clustering because it's got lots of friends, but very few of them are connected, the number of possible connections is going up quadratically, right? So, right? Then they won't count much, right? They're out of they only get one contribution between 0 and 1 to the whole thing. Right? This is averaging over n nodes, and each node's contribution is quite small. So Newman's approach, these are different things. Newman's approach is to measure the number this is a global quantity divided by a global quantity. So it's the number of triangles divided by the number of triples with a 3. All right, so what is this? Am I going to explain all of these things? Yeah, I guess so. Yeah. Well, I'm going to do it on the board, and then we'll have it again because I'm excited about this. Okay, so we've got these guys. If we have a triangle, so that just means a connected triangle. So this is let's say A, B, and C. So these guys are connected. The triples involved here are these pieces. There's this connection. There's this connection here and this one, right? So here if you look inside your network, you see there's a B, A, C, right? That's this piece. There's an I went the wrong way, A, C, B, and a C, B, A, right? These are the triples. And then there's one triangle, right? A, B, C. So every triangle closes, if you like, 3 triples. Right? So you put the number of triples on the bottom, and every triangle closes 3 of these guys. So we multiply it by 3 times the number of triangles, and that'll give us the fraction of triples that are closed. Right? So if you look at any So this gives you a very nice thing. It's more interpretable than the other one, which is fine. They both have features. It gives you essentially the probability if you find a triple, what's the probability that this is closed? So what's the probability that your friends know each other, or a node's friends know each other in the network? Yeah, maybe. Good. Thumbs up. Okay. So you have to count triples. You can, if you think about, there are nice ways to do this in with the adjacency matrix. Oh, God. It's like 600 by 800, isn't it? Terrible. Is that what it is? The resolution on these things?
Something like that.
It is, isn't it? Like, yeah. Right.
Or like 480p.
Yeah, I think it comes out at 600 by 800 when I save it. Yeah, that's pretty sad. All right. Really? Okay. Feels like a Commodore 64 from 1985. Should dig that up. All right, so let's see. Okay, here's an example guy. Let's calculate that. We'll do the whole thing here, right? So C1 is the average fraction of pairs of neighbors who are connected. So we're going to go here, 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 and here. So it's not looking good for A, who has one mate, and then we're just going to give them a 0. Okay. So here it is here. Right. So the clustering for this A, the local clustering, right, here they are. They have one friend. We're going to define that to be 0. When we go to C, they have two friends who are friends with each other. So their little world is fantastic. It's cohesive. So they get a 1. Right? The number of possible connections is 2 choose 1. 2 choose 2, which is 1. And so, right, and that's on. It's the same for D. B has a slightly different situation, right? They have 3 choose 2 right? Possible friendships that could exist. So there are 3, right? And only 1 is in. So there's a third for that one. So 0, a third, 1, and 1. So you add those guys up to give you, and divide by 4 to give you what we're going to call C1, this Watt-Strogatz measure. Okay? Just a little, okay, good. Both of these measures go up generally with each other, but they are not the same. And here's another problematic piece about this. You might think, oh, I'm going to build a network that has a certain clustering. It's really actually hard. That's a really difficult problem. And especially to build one that has a certain degree distribution and a particular clustering coefficient. You want to specify those two and leave everything else to be random. So you want essentially building a special machine that's going to pop out random networks that have these two things defined about it. That's all. Degree distribution is a big deal, but you want the clustering to be a certain number. It's very, very hard. There are some constructions. It took us quite a few years to do that, but they're nasty. So here's one of the problems. You might think, all right, well, I've got this network sitting here, and I'm going to make it have more clustering. All right? So I'm going to make some triangles. Okay, so you say, all right, boom, I'm going to add that guy. So now I've got a triangle. But actually, this is the new one. You've opened up this triple, this triple, this triple, and this triple. So you've created more triples. And you can actually, the clustering goes down, which is upsetting. So that kind of simple-minded way of doing things doesn't work. Clustering comes from actually having, and we'll get to these later on, bipartite kind of a situation. So there's a context in which people interact, lots of connections, or animals, or whatever they are, dolphins. And then there's another one over here, and they interact in this way, and that creates a sort of a local, lots of triangles locally. Okay, so this is how we measure this guy. Okay, so there's one triangle in this network, boom, and the number of triples is quite a few, right? So there's this guy here, there's this one going all the way through, so I've tried to break it apart, and then the 3 corners of this one, all right? So there's 1, 2, 3, 4, 5 triples. Yeah, and as I said, you have some problems. So if you close this one, is that one all right? Okay. Let me just say this. Okay, so we're gonna get a 3 for this one, and then there's a 5 on the bottom. So it's a different number. What do we have? We have 0.4. This is gonna be 3/5. No. We had 1, 1, and a third, So 4/3 divided by 4, a third. All right. No, 1, 1, and a third. It's 8/3 divided by 4 is 2/3. All right, fine. So this is going to be a different guy. This is going to be 3/5. All right. Okay. Okay, I've told you all these things. It's all on the slides. Good. 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 And again, it has this nice interpretation that this is the chance that if you look at any, so if you just take any triangle, this is any triple, it's the chance, if you like, you can think of it as a probability that it will be closed and be part of a triangle, that it will have a socialness to it. Okay, so you can do some other things. You can really elaborate in a lot of other ways. So let's do a little bit of this. Okay. So this is using the adjacency matrix, right? So again, the adjacency matrix, if you have I and j connected, you have a 1 in the matrix there, 0 otherwise. So if there's a path ijl, right? So if there's I, j, and l, if they're connected like this in a path, then you have to have aij times ajl has to be 1, right? So this is a 1 and a 1, simple thing, right? So if there's some break, right, you get a 0 in there, it disappears, right? Fine. We don't want to go back to where we started, so we make sure that I and L are not the same, because we could just go back on our path, so that's a bad thing to count. This is kind of silly. So, but we can, this is just generalizing this. So if we have a path of n edges through the network, then it has to be that, and it goes from I1 to IN minus 1, ending at to IN, then you have to have, it's just a generalization of this, you have to have the product of all of these entries of the adjacency matrix. Yeah, that's good. I was worried about these guys. Okay, so equaling 1. Is that okay? Well, basically, each one has to be 1. And so you can write it down mathematically like this. So gap it all, then we lose a 0. All right. So that's like, this is a little bit of a sidebar here. Okay, so the number of triples in the system then will be, this is quite nice. So let's get it right. So we take a squared, because this guy here is, right, so a, ij, ajl, that is, this guy is, if we sum from j equals 1 to n, right, we're summing over these guys. This is matrix multiplication, right, so it's a times a, and it's the IL entry of the result of a squared. Right, so if this is more generally Bij, Bjl, sorry, Cjl. If we did this, 1 to n, then this would be the matrix B times C, and it would be the IL entry of that. Linear algebra fans? Linear algebra is the best. Matrixology, all right. Okay, so this was, it seemed like a silly thing to do, because we're just, all right, it's, we're codifying this mathematically, but it turns out then we have some nice linear algebra power to back us up. All right, so if you did that, and now we're summing over these middle guys here, well, we also want to sum over I and L to get the total number of triples, right? Because if we sum over I, J, and L, then we'll get the number of triples, right? Because we'll get a 1 if it's a triple, a 0 if it's not. And we just had this one problem, we don't want to count the ones where we go back, because this includes the ones where we go boom, and then boom. That's not a triple. That's a bad triple. Okay, so, all right, this is a squared, it's the IL entry, and then we sum. So we essentially, we multiply A with itself, and then we sum up all the entries inside it. So it's a norm of sorts. And then we're going to subtract off the guys along the, we want to remove the I equals L characters, I equals L counts. And that's very nice. It's the trace of A squared. right? Which is the sum from I equals 1 to n of a squared I, right? So that's the trace. Run down the, just dive down the middle of the matrix.
Don't you also want to get rid of the ones where you go from I to L and then the backwards one of that where you go from L to I?
Okay, yeah. Oh, you mean, okay, good. Right.
That could be.
So that's what this half is.
Oh, okay.
Yeah. Right. So we've double count, overall this has cleaned this problem up, but then we've double counted everything.
Yeah.
Correct. Very good. That was the last piece of the puzzle, was that we could do, yeah, we might do a bad, so this is I, J, and L. So we're going to go this way and this way as well with this counting. Correct. Good. Excellent. And the number, this is just for fun, all right? So the number of triangles is kind of cool. So this is the trace of A cubed. Kind of thinking it's missing something here, but okay, let me see. Okay, so A cubed, so now we want to go around in a circle. So we have IAJ, AJL, ALM, right? So that's going to be back to I, right? So that's I, J, and L. Yep. So this means we went from I to J, and then J to L, and this was the starting point. So start and end. Okay, so there are two ways we can go. We can go this way or this way, and there are three places we can start. So we're going to count each triangle 6 times if we take the trace of A cubed. Right. Because this, right, so summing this thing over I, J, and L, pretty spectacularly, is the trace of A cubed. Right, because it's a product, and a product here that gives us the A cubedness, and then because we have I's matching here, we get the trace. And I'm trying to think about why. Yeah, okay. So we don't have the problem we did with the triples because you can't go like this and come back to yourself. Right, so it's just not in the game. Okay, so you couldn't have I, J here.
The only way to return
Yeah.
back to yourself in 3 is to go through different.
Right, so if you come straight back, it's just you're necessarily not going to. Right, good. So that's kind of fun, right? So, okay, so you can express it then as the whole thing will be 3 times this beast, which will be a half the trace of A cubed on top of this blob, which has got a half in front of it. So the halves disappear, so it's trace of A cubed divided by this thing. So, that's kind of a fun little diversion of math. Okay. But this is the sort of thing, you add a few pieces like this and it empowers you and you can do sneakier things. All right. Okay, so just a bit about these two guys. I mean, it seems like such a simple thing to measure, but anyway, it occupied us for a long time. Let's see. And it's still it remains a very important feature. Okay, so I said this before. So for very sparse networks, then C1, because it's a global average of a local quantity, you have a hub in here. Its contribution is some number between 0 and 1 to an average of n things. You'll see in papers they don't even tell you which one is being used, but this is people often prefer C2. That's what's happened. In general, they're not the same. C1 was a global average, as we said. This is just a summary of a local ratio, and this is a ratio of 2 global quantities. Some nice features. But it gives you a sense of how hard it is to calculate them as well. We know we've got a cube essentially involved. Right? It's a cube of a matrix, which is not delicious, but they are sparse matrices. Right. So is that okay? No unexpected traces.
I don't know what squares. I only do triangles. It's fancy.
Oh, I see. No, so people do. Yeah, you're right. Yeah.
Do that one.
Um,
I've never seen the triangle.
Well, it's because it's you're looking at this kind of thing locally. I think what I'm trying to say here is that people will look at, so so you have these two friends. Here's you. And you have your friends, and you're kind of interested whether they'll connect, right? This is very natural progress in whatever it is, Linux kernels or anything. But there is this possibility as well, right? So this is, there's two friends here. They go to a party and they bring their buddies, and these two start to become friends. And so you can, that's possible, right? So it doesn't fill in like this. It fills actually first in like that. So this work's been done on email networks and lots of other networks now that are evolving. And Georgi Kosinets, who's now at Google, was a student of ours at Columbia, did some lovely stuff on this and was published in Science and showed very nicely how the probability decays as you go down through this sort of right? This is a closure of a square. I mean, maybe this is not quite what you're asking about, but okay. But I'm enjoying myself talking about. All right, so there's a nice feature in here which is, okay, so now we're one more, right? So these guys are all friends and they go to a party and somehow these become friends, right? Before that kind of more natural filling in. So this is less probable than this, which is less probable than this. This is getting to the point, so this is A, B, C, D, E. So this is a friend of a friend of a friend of a friend. So this is 3 degrees away from you. Hold on, 1, 2, 3, 4, 4 even, okay, yeah. This is kind of the limit of your social universe in a way. It seems, if you look at how networks move around, connecting to this person is not much different from connecting to a random person in the network. So that's your horizon. So of course you know your friends. Your friends might tell you something about their friends, of course, right? So you hear about this maniac that your friend knows, right? So you have some sense of these other people that you don't know personally. But this is like my uncle told me about a cat that, and it was his sister. And, this is what, now you're out in that sort of stuff, right? It's like, it's starting to get, yeah. So information flowing through here it gets harder. They're controlling the whole thing. That's true. They invented the web after all, right?
Yeah, sometimes you get like that really good story that you can never tell because like somebody told it to you and like their uncle told it to them and you're like, darn it.
Well, now we can look it up online and see, No, it doesn't always work that way, but it is helpful. Right, I mean, people do this all the time. We're looking at, like, how could you detect the shape of misinformation, right? So something is, if you have a Twitter thing, something spreading through Twitter or whatever else you can measure, how it's spreading, like how this story is being passed along. Do things that are objectively wrong, like there's some way of, or false, it's a lie, purposeful kind of lie. Does it have a different shape the way it spreads to something that's true but possibly boring? I mean, people do this all the time, right? They tweet that, like, Miley Cyrus died or something, right? Like, she's dead, and then people are like, and it's, yeah. But I don't know what, I mean, they're just bored. It's, okay, I'm going to say something about her. And those things spread, and then they get turned off, or the AP thing, right? That was bad.
And that would have a different shape because it wasn't intentional misinformation. It looks like proper information.
Or was
It really looked
information, but it was from a trusted source.
Yeah, which is, right. So maybe, but then that one actually really stopped quickly. So maybe you get a feel for what happened. But that was pretty bad. And of course what happens then is you can't trust the AP for a little while, which which by default people generally trust because they work very, very hard at it, Yeah, so that you get a transition later on in how people react to things. So anyway, but spreading, I guess I'm getting off topic, but the spreading, it's hard to, this is how far away these people are. Yeah, so that's a good question. So that you can observe that something you can measure on different networks, and then maybe you start to say, different social networks, and then maybe you can conjecture something about them generally, or maybe it's just, this is a Twitter network, this is a high school one where I observe people, you know. But you might be able to generally get at some kind of time scale based on the way, you know, the nature of that information source. And this isn't in physical space, so that's a big deal.
Is there work being done on, like, considering the network, the A, B, C, D, E, where A and E connect? You said that that's, like, right now it's unweighted. Is there work being done on
Okay, so that,
weights of those?
yeah, so that's a hard, right, so that was actually built into that work that I'm talking about, because it's a very hard, because this is actually based on email. So in fact, it was weighted, right? So all you knew that was person A emailed person B at a particular time. There was no message, there was no content, you know, privacy thing. Of course, you can do much different things now with Twitter, but to then say that there's a friendship, so that had to be characterized, right? So people are pinging each other. You have to kind of, I mean, we could go into it later on, but you have to then come up with some sort of model of, or some sort of thing that says this is a friendship, or this is the strength of it over this last period of time. So there's always kind of a parameter floating around. You know, you can't just say from email that these people are friends now. Yeah, but you could measure something like the strength of the connection. Yeah. But there was an effort, I mean, he did, you know, to be able to say anything, the effort was to say, okay, there really is kind of a friendship right now for the last 60 days or something. So what's it, right? You have to chunk it in some way. It's a very, very difficult problem which most people avoid talking about. Okay. So good? Yeah? Okay. Motifs. So this is very nice work by Urielon and co. This is, let me see when this was. This must have been, 2002 was in Nature Genetics. Yep. And they did this thing I was talking about before. They said, all right, the degree distribution is what it is. Okay, so I've got a real network. Things are interacting in some way. I'm going to say that this, whatever it is, you know, gene interacts with so many other genes, so I'm going to say this, right? This is the network. This one has 10 interacting partners. This one has 30. You know, the strengths are all sitting there as a problem to deal with as well. But you say, okay, you know, gene A has 10 connections. And so then you pull it apart, right? You say, okay, I'm going to have gene A, I'm going to put it over here, and it's going to have 10 kind of dangly connections. You put it on your bench. And then you pull up the next one, and then you sit there and start wiring them back together. Right. And you do this, and you don't rewire any one to itself, and you shuffle through, make sure everything's nice and random. That turns out to be kind of tricky and hard, but you can do it. So then you make a whole batch of networks that have the same degree distribution, and the nodes in particular, to the extent that the nodes, node A, for example, in the original network, still has 10 friends, if it had 10 friends. But they're just rewired randomly. Right? And then you look for what in these randomized networks is different from the original one. Right? So we're going to say that elephant in the room is the degree distribution. Let's just take it as you know, that's the thing. We're not going to explain where that comes from just yet, but we're going to look at what's different about our network apart from that. Providing we make really nice, clean, randomized versions. Okay. And so they found a couple of things that they highlighted. This becomes a combinatorial nightmare, right? Because you have to start saying, well, let's look at groups of 3 nodes and groups of 4 nodes and groups of 5 nodes and 6. And because of that increase in the number of possible graphs going through the roof, then it's problematic. But you can certainly say, well, here are all the possible ways that 3 nodes could interact. And now it's a let me get rid of this. Right, so let me draw it out here. So it's X turns on Y, which turns on Z, or helps promote Z, but you need X doing that as well, right? So for Z to turn on, this is a very small network, for Z to turn on, it needs X and Y going. But what happens is, so this gets a pulse and it starts up, and so that's X, so this is time. That takes a little while for Y to ramp up. So even though Z is feeling X straight away, it will take a bit longer to turn on because Y has to start going. So it's a way of putting a little delay in there. Now, if X then shuts off, boom, then, let me put it out here, X shuts off, then Y shuts off, and so does Z straight away. So the analogy that actually Alon would give was elevator doors, lift doors for the people who like smaller, less complicated work. So that you put your hand in and it opens straight away, right? And then there's a delay on the other side, providing everything is working. Yeah. Yeah. So this thing appears much in biological networks, right? It appears. That was one of the main observations. It's called a feed-forward loop. It appears in a very statistically unlikely fashion, right? It's relatively very abundant. Okay, and there are different. So it's a motif, right? So these are these little substructures. You see it in electrical networks because it's got some nice features that we've made. You see other ones in food webs and so on. You see, I think the way to say it would be they have kind of master switches. So there's an unusual number of genes that turn on many other genes. And I think in the paper they had a kind of a horrible thicket type thing as well. Many genes turning on many other genes. So that was, yeah. There's some nice work by Chris Wiggins and his team at Columbia to try and go through it very strategically. So this is actually a pretty easy thing to do. You've got a network sitting in front of you. This is messing around, but this is a conceptually pretty interesting. It's easy and interesting thing to do. Aaron Klasser, we've mentioned him a few times. So this is an excerpt from one piece where they knew exactly what was going on. So it's the NCAA football conference, so it's who played whom. But the idea here is you feed into, I was talking about before, you feed into you take your big network of interactions, which are dynamic, right? So, of course, in this case, it's Saturdays, right? So there's a game. Oh, you don't even know it's football, right? But you know that A and B were connected on that day. Right, and then the next week, A is connected with Z or whatever it is. And so you feed all of this in, and you've got this, and I don't know if they did this. They might have just collapsed the whole thing. They might have accumulated the whole thing. So then you feed that network into a box, and you want the box to spit out some kind of structural thing that you can look at, right? And so what it did was said, and these are labeled, and there are boxes here, like these guys are similar to each other, they're connected to each other, so we're going to give them a particular color and say they're a, right, you have to test the so-called modularity, right? This is the word modularity. You want to test to see that this was really a group according to some other parameter, something we get to later on, potentially, certainly in complex networks. So these are all the conferences. So it actually, it matches up exactly with what's going on. There's a classic problem that people always have to test themselves with, which is Zachary's Karate Club. It's a paper from 1977. It's about 32 or 3 people in it. Someone, anthropologist of sorts, just went in and looked at what was going on. This Karate Club turned out to have 2 big factions. And so, you need to, this tiny little network, you need to feed that into your machine, and it needs to kind of do a good job separating those 2 groups. So this is a nice little paragon example. But of course we have many bigger ones to test where we know the real story. Yeah, so clustering was about, so these are, so the words can be a bit mixed up because in percolation you talk about a cluster being actually a big blob like these guys. So that's bad. We're going to say communities or components or something like that. Let's say communities. Or modules. Clustering was simply local, right? So it's just that it's about whether your friends are friends with each other. So that's one piece. This is that's certainly true in here. There's a lot of clustering locally in here. That's absolutely true. But this is something that's a higher level. It's going to come out. These algorithms that people have built, many different types. They want to say, okay, this set, and here, so there are 8 here. They are a community. There's something special about them. There's lots of clustering, which is the socialness, but this is a community. Is that? Yeah.
So in this one, they've got all those dark lines identifying each little community, but how do they know to discount all of those lines between communities?
Okay, so these are just being drawn.
Separates the hairball.
Yeah, these are. We can look up the paper, but I think they might be. I guess I'm saying the wrong. These could, look, they are different thicknesses. So these should be, I mean, ideally these will be the number of times they played each other, right? So it is the strength. But I'm not sure if that's true. I think they could be colored just because these are the links within the community.
Right.
So we've identified this as a community, and then we'll strengthen, we'll make a stronger line basically for each link in that community. And these are all still in there. These were all used. They all went through the algorithm. And then you have something that's, you have a display of trying to present it so it's reasonable. Like there's a bit of a struggle over here. Yeah. So it doesn't throw these away. It's downplaying their importance.
Okay.
Yeah. It's finding it. It's discovering that they aren't connecting. Really strong communities. Yeah. I mean, overall, this thing, if you zoom back out, right, is one big community. Right, there's the badminton thing over here, which is not connected, right?
Not that much crossover.
Yeah, there's not much crossover there, right? So that's that's going to be its own thing. But then you zoom out and you've got sports or something, right? So, yeah. Terrific game. Not trying to disparage badminton, but different to football. Okay. Cricket obviously is different. Okay, this is really a simple, obvious thing. Concurrency. So it matters, the sequence of events, but because we couldn't help ourselves, people just ignored that for a long time and made a network in any old way they could by here are a bunch of interactions. Like all these emails went between people. Okay, so great, let's turn it into a network, right? It might have been over 5 years or 2 years. So very simple, a very obvious thing. Obvious is a tricky word, but this is true in this case, I think. So, just looking at static networks is not enough, but we have had to figure them out. And we've figured out, of course, the dynamics of these networks, how they grow, but this is a property on top, potentially. But it's also, now we're talking about networks that they're not necessarily, you can't even look at a picture of them. It's really a big sequence of pings, like a little bit like the bike example in London that I showed you, right? Really what you're seeing is all these little pings back and forth. And if you want to smooth it, you apply some smoothing to it, you start to see repeated pings. Obviously, it matters where you've been before. The accumulated data network thing is a bit of a problem. So Martina Morris and Kretschmer had a paper in 96. What was that? I have to remind myself what that was. Yeah, okay, yeah. I know she had a paper in Science. All right, so this is now, people are running around talking about temporal networks. This is, now it's framed, it's a thing, and this is what we're all gonna, eat for breakfast for the next couple of years until it's like just nothing left but the skeleton. Maybe there are some beautiful, joyous things to find out. Okay, so, all right, so now it's kind of in the sights, yeah. All right, what else have we got? So this is something that I mentioned earlier, of course, blood networks and river networks. It's something I worked on for my PhD. It's what it's my sort of, when networks were taking off, I was doing this. Turns out there's all this fractal business, like the first fractal stuff in some ways quantified comes from river networks. This guy Horton in 1945 and Strahler later on talked about how they'd, and I'll just tell you this quickly, we revisited in complex networks, it's a lot of incredibly rich, beautiful structure, which, as I said, works for blood networks largely as well. So simple thing to do is say, all right, here's a network. Let's take away all of the little end parts. We'll call them order 1, so they're the dash ones. So we prune them off. And then we look at what's now in this renormalized thing, if you like, or this pruned version. What's order 1? We'll say they're order 2. Take those guys off, and then this remaining one is order 3. Depending on your resolution, mile resolution for the US, you get maybe order 10 or 11 for the Mississippi, right? It's a logarithmic thing. And then you can play all sorts of games, right? So you look at the typical length of order 3 ones versus length 2 versus length 1, and the area that they drain, right? So this drains some area. You get all sorts of nice recursion. You get power law size distributions, of course, because that's what happens. You pick a random point on the network and measure the length to the top and measure how much water is coming through it or the drainage area. And that distribution turns out to be power law. So of course, it's true. We talked about it for scaling relations. Yeah. Anyway, there are lots of things in here. So yeah, people do have done. There's a whole literature on like filling up mice with a particular kind of material and then removing the mouse, right? So you put it into the bloodstream and then you get a nice network to look at, or laying the whole thing out and like counting it and so on. So there are good data sets that were somewhat hard fought for. Obviously, remote sensing would be a good thing here. Okay. Anyway, but these kinds of rules, and there's all sorts of embellishments in here that apply for lots of these distribution kind of networks, or collection ones. I'm just going to give you these things and we'll finish. How are we doing? So there are a bunch of network distances. Again, this is I'm going to really give you them for bare networks, right? Unweighted ones, but you can see they generalize in nice ways, sometimes hard ways. So the shortest path is a very natural thing. So it's the shortest number of steps. Might not be something you can find, right? If you're really running around this network, unless you have Google Maps or something. But we don't really have that in social networks or in information networks necessarily. Chemical distance comes out of polymers, plastics. Okay, great. Average path length this will be a big deal for average shortest path length. Is going to be a nice thing for the small world story. So we'll come back to this one. So this is just the average shortest path in the whole network. So you might ask, so if you have a ring and that's your network, then the average shortest path is large. On a random network, it's quite small actually, because there's lots of mad wiring going on, providing it's got a giant component. There are lots of nice algorithms for calculating these things because, as I said, a little bit of a sneaky thing, right? You have to right? You have I and j, and you have to find the shortest path, and they have to do that for all possible pairs. So it's a good thing to think about. You can handle weighted links as well. All right. A couple of other things. There's a famous, a paper that's been cited a ton that talks about the diameter of the World Wide Web is about 2,000 and how it behaves. I don't think you could ever measure that now, but anyway. So it's the diameter. So you take the maximum shortest path, right? So it gives you a sense of how big this thing is. It's a bit of a brittle measure, but it's something you can look at if you start to attack the network, and we'll get to that later on. If you attack the network, does this thing get longer or shorter? Does it get longer, I guess is the thing, right? So if you start to make it more and more fractured, and in principle, then the network diameter is infinity, if you've cut it in half. Yeah, I was trying to say, cheers. We should just wave to them. We should wave to them. I thought it was rain to start with. Anyway, humans. This is an attempt to deal with the problem that you could have separated pieces in your network. It's a funny looking thing, but basically you take your shortest path, again, just as we had before. If it's infinity, meaning that you've got two nodes that are in different components, then it's 1 over infinity here, so they'll amount to a 0. So you sum up all of these guys, you divide it by the number of possible pairs, which is n choose 2, because you are looking at every possible pair, every pair of nodes, and then flip it back upside down. So it gives you, if this was in meters, it's 1 over meters, and then it's meters again. So it does a bit. It doesn't give you. It gives you something that's okay. That only is infinity when there are no links in the system whatsoever. So this allows you to describe networks that have separate components. All right, that's what this says. Boom, boom, good. Okay. I think we're about to run out of time. Let me see what we've got. Okay, good. I'll tell you this very quickly. So centrality, lots of different things. Degree centrality is ridiculous. It's just the number of friends you have, right? As a measure of importance. Betweenness is pretty cool. So now this is the fraction of shortest paths that pass through I. So you have to find all the shortest paths and then count up at each node how many shortest paths come through it. You can have an edge betweenness as well, where you just like all the shortest paths, so you're on an edge and you light up all the shortest paths that come through you and you say, oh, there are 30, I have a 30, all right? So that's a nice, so it turns out, for example, this kind of network, these guys have huge betweenness Because if you take all the shortest paths between all these nodes and all these nodes, there's some shortest paths between these guys, but they have to travel across there. So it's got a nice effect of that. So if you chop it, so it means that these are important. If you chop this one out, then the whole thing breaks apart. Recursive centrality, so that's John Kleinberg, this is Hubs and Authorities, and that is the Google search story, right, as well. Like, these were invented at the same time. Kleinberg was sitting inside IBM, which is a bit like the end of Raiders of the Lost Ark, right, where it said, thank you very much, they put it in a box and wheel it into a huge storage room. So they said they could, as I understand it, he's a lovely guy, this guy's a lovely guy, maybe someone can pay us and we'll license it out to them. So Bryn and Paige were doing something very similar, in some ways simpler, but same kind of idea, this recursive structure. So if the information is here, things that point to information should point to it, and then it should keep going, right? So that you should, okay. So it's a whole network story. All right. So interconnectedness. This is just one quick example, but basically this is a paper that's argued about. It's got a simple model in it, but yeah, you have the power grid, you have the communication structure. The idea is things break here, goes back and forth, disaster. That's becoming a big topic now. All right, key points. 1990s, when this all takes off, it just exploded. Now there's just too much. It's made complex systems a much harder field. I mean, complex systems always existed, but it really kind of nailed things down. So large-scale, sparse, natural, man-made, evolving, dynamic, and measurable things. That's what we're talking about. And we had physical, interactional, abstract, and the sort of the big categories. But this will just go on forever, as far as I can tell. Anyway, we've got a few of the things sorted out. The big models that are out there, key features, but yeah, much more to do. Anyway, so I'll talk about two of those big models in the next couple of lectures. All right, Pim. All right, thank you for holding on.